Section 16.6, Sound Waves. In this lesson, we will explore several key topics related to sound waves. We will begin with an introduction to what sound waves are and how they travel, followed by a look at the linear wave equation as it applies to these waves. We will also classify sound into different categories based on frequency and examine the characteristics of longitudinal periodic sound waves. Finally, we will define and relate displacement and pressure amplitudes. Sound waves are mechanical waves that can travel through any material medium, though we most commonly experience them in air as the sensation of hearing. As a sound wave propagates, it disturbs the elements of the medium from their equilibrium positions. These movements are not just simple shifts in position. They are accompanied by localized changes in both the density and the pressure of the air. Crucially, these variations occur along the same direction in which the wave itself is moving. To describe these waves mathematically, we use the linear wave equation. For waves on a string, this equation states that the mass per unit length divided by the tension multiplied by the second partial derivative of vertical position with respect to time equals the second partial derivative of vertical position with respect to horizontal position. More generally, for any traveling wave moving at a speed, v, the second partial derivative of the wave function with respect to position equals 1 over the square of the speed multiplied by the second partial derivative of the wave function with respect to time. In the specific context of sound, the variable y represents the longitudinal position of air elements or the variations in pressure and density. We categorize sound waves into three distinct groups based on their frequency ranges. Audible waves are those within the normal range of human hearing sensitivity. Infrasonic waves have frequencies below this audible range. For instance, elephants use these low frequencies to communicate over long distances. Ultrasonic waves have frequencies above the human audible range. These are used in tools like dog whistles, which dogs can hear but humans cannot, and are also vital in medical imaging technologies. Let us look at how a longitudinal pulse propagates. Imagine a long tube filled with gas and a piston at one end. Initially, the gas is undisturbed and at a uniform density. When we quickly move the piston to the right, it compresses the gas directly in front of it, creating a region of high pressure. Even after the piston stops moving, this compressed pulse continues to travel through the tube at a specific speed, v. Throughout this process, the individual gas elements move back and forth parallel to the direction that the wave pulse is traveling. If the piston moves back and forth in simple harmonic motion, it creates periodic sound waves. This motion produces a continuous stream of compressions and rarefactions. Compressions are the darker regions in the diagram where the density and pressure are higher than the equilibrium state. Rarefactions are the lighter regions where density and pressure fall below equilibrium. We define the wavelength, denoted by the Greek letter lambda, as the distance between two successive compressions. These alternating regions of high and low pressure move through the medium at the speed of sound. We can describe the position of a gas element using a displacement function. The displacement s, as a function of position x and time t, is equal to the maximum displacement amplitude multiplied by the cosine of the quantity wave number times position minus angular frequency times time. In this expression, the displacement amplitude represents the maximum distance an element moves from its equilibrium position. The wave number and angular frequency define the spatial and temporal periodicity. It is important to remember that this displacement occurs along the x-axis, which is the same direction the wave is moving. Just as displacement is periodic, the variation in pressure is also periodic. The change in pressure is equal to the pressure amplitude multiplied by the sine of the quantity wave number times position minus angular frequency times time. The pressure amplitude, which is the maximum change from equilibrium pressure, is calculated as the bulk modulus of the gas multiplied by the displacement amplitude and the wave number. You will notice we use a sine function for pressure and a cosine function for displacement which indicates that the pressure wave is 90 degrees out of phase with the displacement wave. This graph illustrates the phase relationship between displacement and pressure. When the displacement of the gas elements is at a maximum, the pressure variation is zero. Conversely, the pressure variation reaches its maximum or minimum peaks when the displacement is exactly zero. This relationship is derived from the physical definition of the bulk modulus, where the change in pressure equals negative bulk modulus multiplied by the partial derivative of displacement with respect to position. Essentially, the pressure is most intense where the gas elements are being most crowded together or pulled apart. To understand the link between volume and pressure, consider a cylindrical element of gas with A cross-sectional area A and A length delta, x. As a sound wave passes through, the two faces of this cylinder move by different distances, labeled S1 and S2. This difference causes the volume of the element to change. The change in volume is equal to the area multiplied by the difference in displacement between the two faces. This volumetric change is what ultimately generates the pressure variations we identify as sound. In summary, sound waves are longitudinal mechanical waves defined by variations in pressure and density. We classify them as audible, infrasonic, or ultrasonic depending on their frequency. Mathematically, we can describe sinusoidal sound waves using a cosine function for displacement and a sine function for pressure. These two descriptions are 90 degrees out of phase. Finally, we can relate the maximum pressure change to the maximum displacement using the bulk modulus and the wave number. To wrap up, consider these review questions. First, can you explain why the pressure variation must be zero at the exact moment the displacement of gas elements is at its maximum? Second, what specific factor determines whether we classify a sound wave as infrasonic, audible, or ultrasonic? And what are the standard frequency limits for the human ear? Reflecting on these will help solidify your understanding of the relationship between the physical motion of molecules and the resulting sound wave.